I recently purchased a smoke detector and noticed a small radioactive symbol on the box, which got me wondering, why are smoke detectors radioactive? Well, in this video, we're going to explore the inside of this smoke detector, see how it works, and understand how radioactive decay is used to detect smoke. Also, stick around until the end, where we'll discuss two related topics or branches: how Geiger counters work, and why atoms with high atomic numbers are counterintuitively small. This video is sponsored by PCB. More on them later, but for now, let's jump right in. When we open up the smoke detector, we find a number of components. Here we have the battery that, of course, is almost always dead and needs replacing. Just kidding, but really. Here we have the piezoelectric speaker, which produces both the alarm as well as this chirp, which honestly is one of the world's most frustrating noises. Next, we have a through-hole printed circuit board, or PCB, which holds just a few basic components and is designed in such a way to be extremely inexpensive. On the PCB, we have the main microchip. And finally, here we have the heart of the smoke detector, a metal cylinder which has vents on all sides to allow air and smoke to flow through. On the inside of this dome is a short cylinder with a metal disc on the top and another on the bottom, with plastic separating and holding them both. In the center of the bottom disc is a small well containing 300 nanograms of the isotope americium-241, which is radioactive and thus requires this symbol on the packaging. Before we go further, it's important to say that opening up an ionizing smoke detector like this one is dangerous and should never be done, not even with adult supervision. Americium is, as we mentioned, radioactive, and while it's inside the metal cylinder, it's perfectly safe. But outside, it's very dangerous, especially if inhaled or ingested. We take it apart, so you don't have to. And with that stated, let's move on. So, how does this radioactive contraption detect smoke? Well, the small amount of radioactive americium-241 emits alpha particles, which are highly energetic, incredibly fast-moving helium nuclei with 2 protons, 2 neutrons, and no electrons, and thus are positively charged ions. How fast? Well, they're ejected from the americium nucleus at around 15,000 kilometers per second, which is about 5% the speed of light, or 2,000 times faster than the International Space Station, or 419,000 times faster than a cheetah. This incredible amount of kinetic energy is what makes the radiation dangerous. By the way, the other types of radioactive decay are beta and gamma decay, which are, respectively, incredibly fast-moving electrons and high-energy photons. However, in ionizing smoke detectors, the americium-241 predominantly generates alpha particles. As these positively charged helium nuclei are ejected at ludicrous speeds, the alpha particles run into atoms in the atmosphere and knock off their electrons, thus creating positively charged nitrogen, oxygen, other gases, and thousands of free electrons. Note that any atom or molecule that has lost or gained an electron is charged and thus called an ion. In fact, a single alpha particle has enough energy to create around 10,000 positively charged oxygen and nitrogen ions and tens of thousands of electrons. This process is called ionizing radiation. A professor of mine once referred to an alpha particle as a bull in a pottery shop. Alpha particles run into everything, thereby creating atomic chaos. Here's a picture of a cloud chamber with americium-241, and in it you can see the paths created by individual alpha particles. By the way, whoever marketed these radioactive smoke detectors as ionizing smoke detectors is a genius, because, let's be honest, no one would ever buy a radioactive smoke detector. But we digress. Outside of this device, these electrons and positively charged atmospheric ions would eventually recombine and become neutral. However, in this contraption, called an ionization chamber, we want to use alpha decay to help us detect smoke. And to do that, we use two metal discs and apply the voltage from the battery across the top and bottom discs such that the top is positively charged and the bottom is negative. As you may know, negative charges and positive charges attract, and as a result, the negatively charged electrons are attracted to the upper positively charged metal plate, and conversely, the positive oxygen and nitrogen ions are attracted to the bottom disk. A flow of electrons is a current, and using the circuitry in this chip, we can measure the current drawn to the top plate, which is what happens under normal conditions when no smoke is present. If you want more exact numbers, the amount of americium in this smoke detector, or alpha source, emits around 37,000 alpha particles every second, resulting in hundreds of millions of electrons being pulled off their atoms, but equating to only 50 or so picoamps of current, which is rather small. This provides a baseline for the amount of current flowing as a result of the ionizing radiation from the americium-241. However, when smoke comes in through these vents and into the cylinder, the environment and circumstances change. Smoke contains a lot of carbon monoxide, carbon dioxide, larger soot or more complex carbon structures, unburned matter, volatile compounds, and a whole variety of other components. Thus, when smoke from a fire, smoldering combustibles, or burnt popcorn is present in the ionization chamber, it intercepts both the alpha particles as well as the ionized air molecules and electrons, thus preventing the electrons from reaching the top plate and positive ions from reaching the bottom plate. No electrons flowing to the top plate means no current is present, and this lack of current is measured by the microchip down here, which in turn triggers the piezoelectric alarm to alert you that there's a fire or that you're bad at cooking. Alpha particles are used in this application because of the three types of radiation, alpha, beta, and gamma. Alpha particles have the largest ionizing potential. In other words, they produce the greatest number of ions and a steady flow of current in the ionization chamber when no smoke is present. Additionally, although alpha particles are ejected with a tremendous amount of energy, they are, in fact, stopped by practically anything. This is because they're helium nuclei, which are much larger than either the beta or gamma particles. Just a few centimeters of air, a thin piece of plastic, or a few layers of skin cells are enough to stop alpha particles. However, gamma particles, or photons, are more dangerous because they're able to travel much further and through much thicker objects, and only dense metals like lead or layers of concrete can stop them. And beta particles can travel through skin, but just a thin sheet of aluminum can stop them. So, let's answer three potential questions you may have. Why is americium-241 radioactive? How is it produced? And finally, are there other types of smoke detectors? Well, americium-241 is down there on the periodic table. It has 95 protons and 146 neutrons in its nucleus, and 95 electrons in its shells. You're probably familiar with the idea that like charges repel each other. Well, here we have 95 positive charges and a bunch of neutrons all glued together by the strong nuclear force. However, the repulsive forces of these 95 protons and their ratio to neutrons makes the nucleus unstable, and as a result, it has a probability to repel 2 neutrons and 2 protons, and thus turn into neptunium-237. In this smoke detector, we have 300 nanograms of americium, which equates to around 750 trillion atoms, and over the course of 432.2 years, that number will have decayed into 375 trillion atoms of americium-241 and 375 trillion atoms of neptunium-237. By the way, Neptunium-237 is also radioactive and emits alpha particles, but because it has a more stable ratio of protons to neutrons, it has a half-life of 2.14 million years. So then, let's move on to the second question. How is americium-241 produced? Well, rather interestingly, it's generated in nuclear power plants with the neutron activation of plutonium-239 and 240 into plutonium-241, and then plutonium subsequently emits beta particles and decays into americium-241. That means that all ionizing smoke detectors have some material that come from a nuclear reactor. By the way, this americium is in the form of americium oxide and has a thin sheet of gold on top for safety reasons. Each smoke detector has such an incredibly small amount of americium that a single gram generated from a nuclear power plant can produce tens of thousands of smoke detectors or more. Finally, is there another way to detect smoke? And the answer is yes. The other most common way to detect smoke is using a photoelectric sensor or light. But there are a variety of ways in addition to these two methods. Photoelectric smoke detectors have an LED on one side of a chamber and a sensor on the other side. However, in this chamber, the light doesn't have a direct path through and thus can't reach the sensor. Additional pieces of plastic are added to the chamber to make it such that even reflected light can't reach the sensor. However, when smoke is present, the particles of smoke deflect the light from the LED, dispersing it in the smoke, and thus the sensor can see a fraction of the light, which triggers the smoke alarm to go off. There are a number of pros and cons to each design of smoke detector. We're not going to cover them here, but if you want, you can read the Wikipedia articles. Two quick things. First, smoke detectors save lives. Replace the batteries once a year. Check that they work, and although one type is radioactive, it's perfectly safe to have in your home. But, as with many things, it's not safe to eat. Second, in our explanation, we simplified the circuitry of the smoke detector's ionization chamber. In reality, the top metal cylinder is also an ionization chamber, and the circuitry senses the voltage of the middle disk and compares the ionizing activity in the top chamber to the reference ionizing activity in the bottom chamber in order to know when smoke is present. Here's a schematic explaining it, and note, some designs have the voltages across the chambers flipped. Next, we're going to talk about two topics that branch from smoke detectors, which are the counterintuitive size of different atoms and how Geiger counters work. So stick around because these are genuinely interesting topics. But for now, let's discuss this video's sponsor, PCB Way. PCBs range from the simple, like this one inside a smoke detector with just a couple dozen holes and traces, to the incredibly complex, such as those inside GPUs with hundreds of components, multiple layers, thousands of traces running inside, and ball grid arrays with thousands of connection points. PCB Way can quickly manufacture any PCB from the simple to the complex, with competitive prices and impeccable standards. Furthermore, PCB Way also offers services such as PCB Assembly, CNC machining, and 3D printing, as well as manufacturing flexible PCBs, such as those found in wireless earbuds. From PCB Way, you can buy standard boards for as little as $5 and complex PCBs from $78 and up. And then a senior engineer will dedicate themselves to ensure perfection in the finished product. Additionally, you can have boards assembled for as little as $30, and you'll work directly with PCB Way's engineers who can send pictures throughout the assembly process. Take a look at PCB Way's website using the link in the description below. Okay, so let's quickly talk about two branches related to smoke detectors: atomic size and Geiger counters. As you may know, atoms are incredibly small. But do you think that as the atomic number increases, the size of the atom also increases? Well, let's check. Here's sodium with 11 protons, and here's americium with 95 protons. When we look at the atomic radii based on empirical measurements, sodium is in fact larger than americium. This is rather counterintuitive because you would think that as we add more protons, neutrons, and electrons, the size of the atom would correspondingly increase. So why is sodium larger than americium? Well, it has to do with the fact that positive charges and negative charges attract with a tremendous amount of force. For example, if 1 gram of pure protons were placed 100 meters away from 1 gram of pure electrons, the positive charges and negative charges would attract one another with 1,500 trillion tons of force, which is equivalent to the force of 440 billion Saturn V rockets. Rather unimaginable, huh? A similar force occurs in an atom. In americium, there are 95 protons, and they hold on to these 95 electrons so tightly that the radius of an americium atom is only a tiny bit smaller than the size of sodium. Here's a 3D representation of the periodic table, and the height of each element shows how large each atom is. The size jump in atomic radius from, for example, argon to potassium is a result of the increase in the number and configuration of electron shells, whereas the increase in radius down each column is due to the inner shells of electrons repelling outer shells. And the decrease in radius from left to right is due to the attractive force between the protons in the nucleus and the electrons in the shells. One interesting note is the americium-241 is slightly smaller than sodium, but has almost 11 times the number of protons and neutrons, and due to this, americium is 14 times the density of sodium. This trend in density applies to many other elements as well. In fact, here's osmium. It has a rather small atomic radius and is the densest of all the naturally occurring elements. To finish up this episode, let's briefly branch out to Geiger counters. In short, Geiger counters' fundamental principles are similar to smoke detectors. In this tube, we have an ionization chamber. Radiation enters through this window made of mica and knocks off electrons from the gas, typically argon. We apply positive voltage to a central rod and then negative voltage to the surrounding cylinder. And as a result, the ionized argon travels towards the negatively charged wall, while the electrons travel toward the central rod. The voltage used is much stronger, at around 500 to 1,000 volts, and this higher voltage creates an avalanche of ionization, which is required to detect beta particles, as they don't have nearly as much ionizing potential as alpha particles. Then we measure the current. And when there's a spike in current, that means some radiation particles entered the window and ionized some gas in the chamber. There are a lot of other design elements to Geiger counters, but because the fundamental principle is similar to smoke detectors, we thought it interesting to mention. That's pretty much it for smoke detectors, atomic sizes, and Geiger counters. We believe the future will require a strong emphasis on engineering education, and we're thankful to all of our Patreon and YouTube membership sponsors for supporting this dream. If you want to support us on YouTube memberships or Patreon, you can find links in the description. This is Branch Education, and we create 3D animations that dive deep into the technology that drives our modern world. Watch another Branch video by clicking one of these cards, or click here to subscribe. Thanks for watching to the end.